The deepest hole on Earth is 12 kilometers deep. It's called the entrance to Hell, and it's located in northwest Russia. It was formed by an underground explosion that occurred at the end of the Cold War, when a runaway nuclear chain reaction created a massive gas cloud. Then it all blew up. The shockwave from the blast was so powerful that it was recorded by seismometers as far away as Norway and Scotland. But despite its hellish name, scientists don't think this gaping chasm is anything too dangerous. Even if we dropped a thermonuclear bomb down the shaft, it wouldn't blow up because the explosion would be absorbed by the dense rock below the surface. In fact, dropping a nuke into the deepest hole on Earth might not even cause any harm at all. That's because all around us, beneath our feet, there's a vast molten core made of iron and nickel, hot enough to melt lead. So if a couple nukes go off down there, it won't do much except add a little radiation to our planetary blood. But what if we could dig a hole even deeper, like take a drill and punch through the entire planet? What if we somehow managed to create an artificial entrance to the center of the Earth? Would we unleash a supervolcano that would kill everyone on Earth? Before we can answer that question, we need to talk about volcanoes. When you hear the word volcano, you probably imagine something like Mount Vesuvius, which blew up and destroyed the Roman city of Pompeii 2,000 years ago. But the majority of volcanoes are much less violent than Vesuvius. Most volcanoes are categorized as dormant, meaning they haven't erupted in hundreds or thousands of years, but scientists believe they will erupt again sometime in the future. The reason most volcanoes stay dormant for so long is because the magma deep under their surface is very viscous, which means it's thick and sticky. The magma can't move easily through the narrow passages below the Earth's surface, so it builds up pressure over time until it finally erupts. If the magma were less viscous, it could escape through the narrow passages below the surface, releasing the built-up pressure before it had a chance to get very explosive. In other words, the stickier the magma, the more explosive the eruption. But there's one substance on Earth that has the power to turn sticky magma into runny lava, water. That's why when a volcano erupts underwater, as in the case of the Samalas volcano in Indonesia, the eruption is much less explosive than when a volcano erupts above ground. For example, the 79,000 cubic kilometer eruption of Mount Pinatubo in the Philippines in 1991 released 800 times more sulfur dioxide into the atmosphere than the 1,500 cubic kilometer eruption of Krakatoa in Indonesia in 1883. And yet, Krakatoa was 130 times more explosive than Mount Pinatubo. That's because Mount Pinatubo had way more water mixed in with its magma, which lowered its viscosity and reduced the explosiveness of the eruption. So if we want to reduce the explosiveness of an eruption at the center of the Earth, we need to find a way to bring its magma up to the surface without letting any water get in the way. This is extremely difficult because water simply does not mix with magma. That's why deep ocean trenches, which are formed where tectonic plates collide, usually have mountains in the middle of them. The denser oceanic plate gets pushed under the continental crust, but it doesn't melt right away because there's no water present to lower the melting temperature of the rock. Only when the oceanic plate reaches depths of 660 kilometers or more, where the temperatures reach 1800 degrees Celsius, does the intense heat break down the rocks and release the water trapped inside them. The water then mixes with the molten magma and creates magma chambers that can span hundreds of kilometers in size. These giant blobs of magma eventually force their way up toward the surface, forming mountain chains as they go. But the journey from the center of the Earth to the surface is still pretty slow. Magma can spend tens of thousands or even millions of years moving upward. And we can speed up this process with something called fracking, which is a controversial technique used in the petroleum industry to extract oil and natural gas from shale rock. The basic idea behind fracking is to drill a well into the shale, then use a high-pressure fluid called the fracking fluid to crack open the rock and release the oil or natural gas trapped inside. This is actually a pretty good way to turn thick, sticky magma into thin, runny lava, because the process of cracking open the rock also heats it up. And heat is one of the best ways to lower the viscosity of magma. Now, obviously, we can't just start drilling into the center of the Earth. The deepest hole we've ever drilled is the Kola Superdeep Borehole in northwest Russia, which reaches a depth of 12 kilometers. At that depth, the temperature reaches 180 degrees Celsius, hot enough to melt lead. So we'd need some kind of advanced drilling technology that could withstand those extreme temperatures. But even then, we'd only be halfway to the center of the Earth. To get to the center of the Earth, we'd need to drill a total of about 6,400 kilometers. To put that number into perspective, if you laid the world's longest continuous road, which is over 32,000 kilometers long, end to end 19 times. That's how far we'd have to drill to reach the center of the Earth. But drilling that deep would only take a few minutes because the further down you go, the faster the rotation speed of the Earth itself. At the core, the rotational speed is over 27,000 kilometers per hour. So let's say we managed to invent some kind of drill that could withstand extreme temperatures, and we used fracking to turn the sticky magma into runny lava. What would happen next? Unfortunately, what happens next depends largely on how we manage to get the magma out of the hole. If we leave the magma in the hole, it will quickly cool and solidify, forming a plug that will prevent any more magma from coming up. But once it solidifies, that plug will be incredibly hard to remove because now it's surrounded by solid rock on all sides, and unless we have some kind of really advanced drilling technology, removing the plug will be impossible. But here's the thing. Once the plug is removed, the pressure holding back the magma will dissipate, and the magma will spill out of the hole and onto the surface. Now, depending on the composition of the magma, it could either harden relatively quickly, or it could spread out and travel quite a distance before hardening. Either way, the result will be a volcanic eruption, which is bad news for anyone living nearby. If we want to avoid a volcanic eruption, we need to figure out a way to keep the magma flowing after we punch through the center of the Earth. One way we could do this is by creating a channel that the magma could flow through, but that would require some kind of pumping system that could move the magma at a rate that matched its flow. Otherwise, the magma would simply build up in the channel and stop flowing altogether. And since magma is highly viscous, it would quickly harden in the channel and create another plug, restarting the whole cycle. So if we want to drill a hole through the center of the Earth without causing a volcanic eruption, we need to come up with a better solution. One possibility is to use a continuous flow drilling system, similar to those used in the petroleum industry to extract oil from deep underground. The basic idea is to use a rotating drill bit to drill a hole through the rock, while simultaneously pumping a drilling fluid down the drill string to cool and lubricate the drill bit. The drilling fluid also carries rock cuttings to the surface, allowing the drill bit to keep drilling. If we used a similar system to drill a hole through the center of the Earth, we could pump a special drilling fluid that would both cool and solidify the magma, turning it into a kind of magma slush that could be pumped to the surface. But there's a problem with this approach. We need to pump a lot of drilling fluid into the hole to keep the magma flowing, like over 10,000 times the flow rate of the Mississippi River. And even then, we'd only be able to pump the magma about 5 kilometers up before it hardened and stopped flowing. This is because the pressure pushing the magma up from below is insanely high. By the time the magma reaches the top of the channel, it would be traveling at over 175 kilometers per second, over 5 times the speed of sound. And since we couldn't maintain a high enough flow rate to keep the magma from hardening in the channel, we'd eventually run out of drilling fluid and the entire shaft would solidify, turning into one giant volcanic plug. So unless we can figure out a way to pump the magma continuously and at a high enough flow rate, we'll never be able to drill a hole through the center of the Earth without causing a massive volcanic eruption. And given that the magma at the center of the Earth is hotter than the surface of the Sun, it's unlikely we'll ever be able to develop the technology necessary to pull this off. That means our best chance of seeing the inside of the Earth is to wait until a volcano erupts and gives us a glimpse of the fiery abyss that lies beneath our feet. It's me. And if you want to help support the channel, you can join our community on a crowdfunding platform.